Hello, my name is John Boone from UC Davis, and this talk is entitled The Relationship Between Photon Count, Dose, and Image Quality. And so after a brief introduction, we'll talk about an integrated CT image quality dosimetry phantom that a number of groups have been working on, and then talk about ways that we can improve dosimetry both by incorporating the scan length as well as the patient size into that computation. And then we'll talk about some of the promise of photon counting detectors, which might lead to lower dose CT scans, and then a quick summary. So slide 3 shows the increase in CT utilization for a number of different years, and we can see that the inflection points on this graph really reflect technological developments in CT. In 1990, with the development of helical CT, which made more rapid scans possible, and then later in 1998 with multi-slice CT, which again improved the efficiency of CT acquisition, more slices per unit time, much quicker scan times. So this utility really has led to increased number of CT scans performed in the United States and other countries. Just a snapshot of some of the metrics from UC Davis taken about 10 years ago. CT scans as a function of age, and you can see in the outpatient setting on slide 4 that females and males have reasonable distributions here. Females have larger numbers for whatever reason. But in the emergency room, and UC Davis is a very busy trauma center, you can see that males dominate the visitation and the CTs that they have. And there is a large bump at around age 20 when young men start to drive, and the females tend to be in their cars and are injured as well. So a younger population than you would think when you have a busy emergency room, as this slide shows. So total CT usage from 1998 to 2005, you can see the age distribution here, and most of it's in the age 40 to 60 bracket, but there is a bump in when you have a busy trauma center in the early 20s as well, as this slide demonstrates. So let's discuss an integrated CT image quality phantom, and this is really how we can help manage radiation dose in CT, and this is one of the opportunities we think to improve our understanding of what the CT dose is. And really this is an effort that combines group efforts from the International Commission on Radiation Units and Measurements, specifically the ICRU Committee on Image Quality and Patient Dose in CT, by the Image Gently campaign, which featured initially on CT utilization in the pediatric population, and by 2 task groups of the American Association of Physicists in Medicine, Task Group 200, which focuses on a CT phantom, and that was joint with the ICRU Committee, and Task Group 204, which focused on methods for pediatric CT dosimetry and making that more accurate. So existing phantoms use the CT 100 paradigm, and that's where you're using a 15 centimeter thick phantom that's typically 32 centimeters in diameter, and it is constructed of polymethyl methacrylate, PMMA, which has a density of 1.19. And we make measurements in various holes in this phantom using a CT dosimetry probe, which is 10 centimeters or 100 millimeters long. So one of the limitations of this phantom is that it's only 15 centimeters long, and obviously a patient is much longer than that. And some computer simulations shown in the lower right of this curve show that the CT scatter tails actually extend many hundreds of millimeters in both directions from the actual scan point. And so 40 centimeters length in terms of a phantom is required to capture at least 98% or so of the radiation dose from the scatter tails. And so what this suggests is really a bigger phantom, a longer phantom is necessary to do this. And working through TG, APM Task Group 200 and the ICRU committee, we have developed this 60 centimeter long phantom. It's made out of polyethylene, which has a density closer to tissue. It's about 0.95. Because it is still heavy because of its length, it's chopped up into 3 individual sections that are more manageable, and you can see a picture of the gross phantom in the upper right of this slide 11. And this is 30 centimeters in diameter. So one of the ideas of this phantom is that it would have these 3 sections have different modules that can be used for both dosimetry and image quality assessment. So it's an integrated CT phantom for both dosimetry and image quality. So it has, the center section has a modulation transfer function module that allows us to measure the spatial resolution of the scanner. And the left section on this slide 12 shows a homogeneous area of the phantom which can be used to measure the noise power spectrum resulting from a CT scan. And there are holes drilled in this that to allow the dosimetry probes to be positioned both at the center and periphery and at another point radially in the phantom. So here are some pictures of a prototype of this phantom, and the upper left picture on slide 13 also illustrates the so-called thimble chamber that we are proposing to use, getting away from the 100 millimeter chamber that has been historically used to do CT dosimetry for the last 30 or plus years. So the MTF tool allows a straightforward measurement of the line spread function, which can then be used to compute the modulation transfer function. I won't say more about that. Here are just examples of this for different kernels in the XY plane, and of course the MTF also has values along the Z dimension, and that's on the lower right plot here, and you can see that thinner slice CT images produce better MTFs, as you would expect. So with respect to the assessment of the noise power spectrum using that homogeneous component on the left side of this large phantom, we can scan through the phantom. We can read out the dose. During the scan, we have a chamber at the center of the phantom. We read out that dose, and then we adjust the MAS to deliver the desired dose. In this case, we can use an example of 10 milligray at the center, and we scan again, and that allows us to produce a series of images at a known and prescribed radiation dose to this phantom. That allows us to make comparisons between different CT scanners of different manufacturer and different types within the same manufacturer, also to make temporal measurements from time points 1, 2, 3, and so on for the performance of a given scanner. So we can compute the 2D noise power spectrum, but preferentially we really want to calculate the 3D noise power spectrum using little cubes of data that we can then perform Fourier analysis on in 3D and assess the noise power spectrum. So I have some examples of that, and in this slide we show 3D noise power spectrum, the 3 different views of the 3D noise power spectrum. The axial view is in the upper left in these colored plots. It turns out that there's a lot of data here and it's a little bit complex to display, but I'll just point out that the units of the 3D noise power spectrum are HU squared millimeters cubed. Well, we can actually, because of symmetry, we can do some radial averaging along the in the axial plane, and shown on this slide, and we still have a 3D noise power spectrum, but if we collapse the frequency domains in the X and Y dimensions, we can collapse that to a F of R dimension, as we see on this slide. And so this is still a 3D noise power spectrum, but it's now shows you the noise power spectra as colors in this 3D plot. Vertically the Z frequencies, and radially or horizontally the radial frequencies here. We can then also integrate this and integrate over the Z-axis, the frequency Z-axis, and collapse this to a 2D noise power spectrum as you see in this slide. And the units of the 2D noise power spectrum are Hounsfield units squared, millimeters squared. And what's nice about this as a function of FR is that the area of the curve actually represents the noise variance in the image. And so at the same radiation dose levels, you can see a thinner slice, the 1 millimeter slice here, compared to the 2 millimeter slice, has twice the area approximately, and that's what you would expect. And the other slice thicknesses have less and less noise. And this plot illustrates that as you go to thicker slice reconstructions for the same acquisition techniques, you get lower noise levels as you would expect. We can also vary the dose levels used, and you can see that when you reduce the MAS by a factor of 4, thereby reducing the radiation dose by a factor of 4, the noise variance goes up precipitously as well. So the whole idea behind this phantom is that it's a simple phantom. Instead of the old area where phantoms were complicated and had structure in it that cost money to manufacture, in those old phantoms the analyses were basically eyeball determinations of noise and spatial resolution, and the results were largely perfunctory. The new era of CT noise assessment and image quality assessment we think is really a more simple phantom that's less expensive. It's almost homogeneous polyethylene. These analysis is more sophisticated. We use modern mathematical tools well known to image scientists, and we find that these results, because they are quantitative, they're also very useful for comparing between CT scanners. On this summary on slide 24. So let's talk about dosimetry now. Here we are on slide 25, and we'll first talk about the length aspect of dosimetry. Well, this slide, 26, shows dose profiles as a function of scan length, and this is for the exact same techniques. And these data were derived from Monte Carlo simulations. And so a thin slice has a certain amplitude, but as that slice gets wider, you can see on this slide that not only does the profile get wider, of course, but the amplitude grows, and that's, of course, due to the fact that the scatter tails are adding up in these wider scan lengths and contributing to higher dose levels, especially at the center of the figure. So if we look at dose as a function of scan length in this slide, we can see that the dose at the center of the scan increases and at some point reaches an asymptotic value of what's called the equilibrium dose. So this is dose at the center of the field of view as a function of scan length, and you can see as the scan length reaches 500 or so millimeters that the equilibrium dose is essentially met. The line becomes flat or asymptotic. So we can make measurements of this using a real-time probe that has a very fast readout capabilities idealized in this drawing on slide 28. And so this is essentially the ICRU method, the International Commission on Radiation Units method, which goes beyond the APM Task Group 111 methodology. It really provides the same data, but provides it in a more efficient fashion. And so you place a real-time probe at the center of this very long phantom and do a helical CT scan through it, and you get a curve that looks something like what you see at the bottom of slide 29 here, a profile. And that profile shows that you're measuring initially scattered radiation when the beam is well away from the measurement volume, and then as the beam progresses through the measurement, you measure scatter plus primary, and then as the beam moves on from that, you're measuring scatter again, and that essentially describes the shape of that curve. So with this one curve, however, we can integrate the beam profile with different thicknesses, and we can generate that so-called H of L curve as a function of scan length, as you see in the upper right plot on slide 30 here, and that works very well and is quite efficient use of scanner time and medical physicist time. And so from this curve, now seen on slide 31, we can generate different correction factors depending upon the scan length that was actually used on a given patient. And so these are not the correction factors per se, but this data can be used for generating correction factors. So now we address the patient diameter dependence of CT dose, and slide 33 illustrates the situation. The CTDI vol is really measured on a very large polymethyl methacrylate phantom, which is 32 centimeters in diameter and has a density of 1.19. This is equivalent of a person with a 47-inch waistline, someone over 300 pounds. Whereas the average patient at UC Davis, I made some measurements of this some years ago and found that the average patient had an effective diameter of about 28 centimeters, corresponding to a 34-inch waistline. This analysis was for both men and women in a cohort. And the real issue is for the same technique factors on the scanner, smaller patients, shown here in slide 34, will have a higher radiation dose than larger patients and also the large phantom. So TG204 focused on pediatric CT dose and really combined data from four independent research groups, from Cynthia McCullough's group at the Mayo Clinic, Tom Toth and Keith Strouth working together in the Boston area, Monte Carlo studies performed both at my group at UC Davis and by Mike McNick-Gray at UCLA. This data was put together in sort of like a meta-analysis, not exactly that, and we used the effective diameter, or the water equivalent diameter, as essentially the metric by which to normalize the data. And you can see the conversion factor as a function of effective diameter from data generated by these four independent groups fall amazingly along a line that has some curvature to it. It's not a perfect fit, but a reasonable fit. And so this best fit line, the black line shown here, is essentially the conversion factors when the 32 centimeter diameter phantom is used to compute 32 CTDI vol. So the idea is that you assess and find what the effective diameter of the patient is. You look to this curve for a conversion factor. You multiply that by the CTDI vol reported for that patient's scan, and that is a better estimate that takes into consideration the patient's size of the mean dose in the scan volume for that patient. And here are just examples of the large tables of conversion factors that are available in TG204, which is freely available on the web. And so these measurements can be taken from the scanogram, just a lateral measurement as shown in the slide on the left, slide 39, or from bilateral measurements as you see on the slide on the right. So finally, looking forward to new technology that everybody is anticipating in the CT world, and that is using photon counting CT detectors instead of energy integrating detectors. The current CT scanners and most X-ray detector systems in general are energy integrating. They don't count photons photon by photon as is done typically in nuclear medicine cameras, but rather X-ray systems tend to integrate, and that's because of the large flux that's used in X-ray acquisition. But now detector technology is becoming sophisticated enough where photon counting detectors are possible, and there's a lot of literature on photon counting papers recently. And one of the real benefits of photon counting detectors is that you can tend to overcome the electronic noise that dominates in energy integrating scanners. So if you look at this log of variance, which is noise, as a function of log of the fluence rate, as long as you're at high fluence rates on an energy integrating system, the quantum noise dominates, and where A of Q is greater than A of E, Q is a quantum noise and E is electronic noise. But if you're at lower fluence rates, the signal levels generated by the X-ray flux are not as high, and the electronic levels of noise can actually overwhelm the signal generated by the quanta, and in such case you really are suffering from electronic noise, and this is quite visible in both fluoroscopic images, CT images, and radiographic images. One of the limitations of photon counting detector systems, however, is that they tend to become paralyzed at high count rates, and you have these dead time losses, so the actual signal might extend as this dotted red line, but you would be measuring essentially a signal corresponding to the solid blue line. And so this slide compares photon counting detectors with energy integrating detectors as a function of photon fluence rate. And we can see that the blue line, the photon counting detectors work great at low fluence rate levels, but tend to become paralyzed at high rate levels, high flux levels, and that's where they become less usable. Energy integrating detectors, on the other hand, suffer from electronic noise at low fluence rates, but then perform well at high fluence rates. And so the hope with photon counting is that we can overcome some of this electronic noise, and that'll allow us to reduce some of the X-ray doses without the addition of this of the electronic noise. So another benefit of energy selective photon counting, as shown on slide 45, is that we can actually measure different energy bins, and we can do selective energy weighting. And we could also do dual energy subtractions, as you see on slide 46. And this image on the upper left shows a combination of iodine and calcium imaging. On the lower right image, you can see how dual energy imaging is used to render gout in this severely afflicted patient's feet. Energy decomposition will have some value in CT when we get to this photon counting reality. Currently, there are CT scanners that can do dual energy imaging in an energy integration mode. So in summary, we hope to have a reality in the near future where physicists can use a combined dosimetry phantom with an integrated CT image quality phantom. It will allow an analysis where we will know the radiation dose and can quantify the noise properties in that setting, very similar to the well-utilized DQE, detective quantum efficiency, used in planar radiographic imaging. We can't do that in CT for various reasons, but if we measure the noise or the noise equivalent quanta at equal dose levels between measurements, which is what this phantom allows, we can essentially come to the same utility as a DQE used in planar radiographic detector systems. For more accurate CT dosimetry tools, we have dose conversion factors that take into consideration scan length corrections, and also that take into consideration the patient size correction. So we hope that these phantoms and the techniques discussed in this talk will lead to better dosimetry, and knowing the doses, we'll be able to do protocoling such that we can reduce radiation doses when and where appropriate. Thank you.